the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence. Waste of existence. We spend our life searching for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence. Waste of existence.
The sun is shining and the anxious earth is rising. Anxious earth is rising. I'm so happy.
Spend our life searching for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence.
Hey, hello, hello, hello. That's our new opening. YouTube didn't like our old opening for some reason. I'm only getting one channel. I'm only getting the right channel here, so I don't know if that's me or what. Let me do a sync test here, because we all got to start with a sync test. Alright, that's close enough. It's not exactly, but close enough, I guess. We just don't read my lips. Alright, this is Double Triple Channel on Twitch. It is September 1st. September on Twitch. But sadly, I won't be able to participate because I'm not an affiliate. All right. Well, I guess it takes a while, right? It takes a long time to do that. You got to build it up slowly. So my name is Ron. I live in rural New Hampshire. I live in a rural area with forests all around me and lots of wild animals and stuff. So I talk about that kind of stuff. I talk about New Hampshire sometimes. Sometimes I talk about the animals. Usually, though, I talk about science and technology, which is what this stream is all about. I also I do IRL sometimes. I'm vegan, so I talk about that sometimes. And I do news, a lot of different stuff. Variety streamer, I guess they call it. So that's what I am. But mostly science and technology. That's what I try to focus on. So, yeah, time dilation. and why astronauts age less or more depending upon where they're at. And there's a paradox. You may have heard of the paradox where there are twins and one stays on Earth and the other one flies away and comes back, and one of them's older than the other one. And how does that happen? How can that be? You know, that kind of stuff. Occasionally you see it on a lot of times you see it on sci-fi movies. You know, we did a thing on Interstellar the other day, which talked about time dilation. That was a little bit different. That had to do with gravitational time dilation. Today, I think I want to focus mostly on time dilation that happens from different in reference frame. In other words, one person going fast or traveling along at a speed, and another person relative to that person being still. You know, and when that happens at high speeds, speeds here on Earth, we don't notice it. But when it happens, when like in spaceships, when they go really fast, then it can become noticeable. And the faster that a spaceship gets to the speed of light, the more that time dilation effect comes into effect. You know, now nothing can go as fast as the speed of light, except light, or nothing. Let's say it this way: nothing can approach and get to the speed of light that has mass, and anything that doesn't have mass always travels at the speed of light. That's just the way physics works. Maybe one day I'll explain that one. There is an intuitive explanation for that one, believe it or not. All right, let me see if I'm gonna do a lip sync test here just to see what we're doing. It's pretty good. It's pretty close. Yeah, we're all right. So what I wanted to do was to try to get some find some videos, you know, that kind of did that. Oh, I didn't tune up my camera here. Maybe I should do that, huh? This looks okay, doesn't it? For what I'm working with. Let's see here. I'll see if I can make it better. Whoops, did I make it worse? Let me see here. All right, give me a little bit of that. That. This happens at the beginning of the stream. I noticed that a lot of streamers do this, so it's not just me, I guess. You know, I'm not the only one who fiddles around with stuff at the beginning of a stream. Let me see if I can get it into focus here. All right. Now I'm looking at my monitor right now to try to get it into focus. Get me into focus and get the background out of focus. That's what all the. Let me see. Did that do it? All right. Let's try that and see if that works. Did that work? I guess that's okay. Yeah, I notice a lot of streamers do that, so it's not a big. I thought maybe I was just dumb or something, but yeah, a lot of them do that. Some of the streamers that are, you know, have their own. You know, they have like a friend or somebody they hire or whatever to do the technical stuff, but it's just me, so I got to do the technical stuff and figure it all out myself. But that's okay because I'm kind of a technical person anyway. So there's let's see, there's one more thing that I should do. No, it's okay. I'll just remember that. All right, I think we got it. So what happens is they've actually measured this. First, Einstein figured this out, or actually Lorentz figured it out first. Yeah, guy named Lorentz. What was his first name? Hendrik Lorentz figured out this gamma effect, or Lorentz. In fact, when Einstein first came up with his theory, they called it the Lorentz-Einstein theory. And then later on, somehow Einstein got the credit on that. I don't know how that worked. But yeah, it was Lorentz. Lorentz figured out the actual math for the Lorentz. He did a Lorentz transformation, and he figured out this thing called gamma, which is the amount of difference. But then Einstein kind of put it in, took it all and put it into a form that was easy to understand, and he added more stuff and put more details around it and stuff like that. So he got the credit for it. But he also, after that, he did what's called the special theory of what we now call the special theory of relativity, which is what I'm going to talk about here, which is the time dilation. When when astronauts go up in space, why do they not age as quickly as people on Earth, right? And part of that has to do with this speed. When something is going at a speed, if you're at rest and something else is traveling by you at high speed, to you it looks like their time is going slower, but to them it looks like their time is all right and your time is going slower. And when you work it out, that's kind of a paradox, right? How can one be? Because when they get back on Earth, one of them has to be slower, or you know what I mean? Can't be both of them are slower than the other when they're back in the same spot. So that's the paradox, and there are lots of even to this day people are trying to figure out and trying to understand how that works, and there have been dueling YouTube videos from these science communicators, one saying, oh, it's acceleration, or it's this, or it's that, or and it's a change in reference frame, and they got all these different ideas as to why they think the twin paradox happens. So that's what I'm going to talk about. But first, I'll talk about special relativity, and then Einstein. Right? Einstein said that special relativity was his first thing. He figured that out, and then he said, "Oh, wait a second. This is a much broader thing that has to do with acceleration, and acceleration has to do with gravity, and he came up with this whole thing, this general theory of relativity that talks about gravity and the bending of space-time, which space-time was something that Minkowski came up with. It's taking our space, right, which is 3 dimensions. You got up and down, right and left, forward and backward, 3 dimensions, right? But then if you take time as a 4th dimension, then you can put that in there, and it's 4 dimensions, and they put it all into one thing called space-time. And it turns out they're all fluid. You can bend space, you can bend time, it's all a fluid thing. And Einstein figured that all out. He came up with these equations called Einstein's field equations for general relativity. And I don't understand. It's pretty complicated stuff, but there are like 16 of them, but they map into fewer than that, and 10 rather, but they map into 16, I think it is. So that's complicated. I'm going to talk about that. I'm going to talk about just regular time dilation, because something is going faster than you are, and you look at it and it looks like their time is going slower. And there are a bunch of videos out there that try to explain it, and I went through and I tried to find them, and let me see if I can bring those up here. I kind of make some changes to my thing here for that new opening. YouTube didn't like that I had an opening that had copyrighted stuff on it, so I had to change that. Unfortunately, let's see here. Okay, there we go. Oh no, that's not it. Alright, there it is. Oh, I've always wanted to try this. Can I do this? Yeah, I've always wanted to try this. Let me see here. Isn't that cool? And then it goes back, and then it goes infinite regression. That's kind of cool. Alright, let me fix that. Alright, somewhere here I've got show prep, and I put some stuff in here. Here we go. Let's see if this comes up here. Real time. There we go. Okay, time dilation. All right, this is kind of small. I don't know if I can make it bigger. All right, so this is David Butler. He also, I think he also does the Fermi stuff. I recognize his voice, but he released this on Creative Commons, so it's okay for us to look at this. And this is a real simple thing that explains why, on a real basic level, why time dilation happens. And there are some assumptions that Einstein made, and that turn out to be true. And one of them is that well, the laws of physics are the same everywhere. That was an assumption he made. The other more important thing is that the speed of light is constant. It's always the same for all observers in all reference frames. So even if you're going really fast in a spaceship, the speed of light will always be the same, which is about just under 300,000 kilometers per second, which is real fast. And nothing can go faster than the speed of light. And one of the weird things about that is that if you add speed, like if you're in a car, right, and you're going along in a car, and then you shoot an arrow at the front of the car, you add the velocity, right? You take the speed of the car. If the car's going 50 miles or 50 kilometers per hour, you shoot an arrow at 50 kilometers per hour, then the arrow would go in 100 kilometers per hour with reference to the ground. But it turns out if you go to real high speeds and you go close to the speed of light, suppose somebody's in a spaceship and they're going the speed of light, and then they shoot a light out of the front of their let's see. No, yeah, let's suppose they're going at 0.8 of the speed of light, right? 80% of the speed of light. And then something leaves that spaceship and goes 0.8 speed of light from this one. If you added those together, that either one of them can say, well, I'm not going speed of light, right? But if you add them together, then it's 1.6 the speed of light. It would go past the speed of light. So there's like a barrier there. The speed of light is a barrier, and you can't add things up to get to that, to get beyond that barrier. And it turns out there's a real simple, kind of simple formula that Einstein or Lorentz worked out for that. So let's watch this little thing here, and this guy kind of explains why that is, and then we'll talk about it, and maybe it will. One
of the most unusual consequences of the speed of light being a constant for all observers is that the flow of time itself is not. One of the most unusual consequences of the speed of light being a constant for all observers is that the flow of time itself is not immutable. It too must be relative to the inertial frame's motion. Here's a good way to see why this must now be the case. Here's a simple light clock. Light travels between mirrors at the end of a known length. For our purposes, we'll make it a very long length, say 150,000 kilometers. That way, one round trip will mark 1 full second. Now, if we put the clock into motion with respect to a ground-based observer, we see that the light has to travel further. And because its speed is constant, it will take longer. The moving light clock is therefore running slower than a stationary duplicate. This is called time dilation. It's the geometry of the situation that gives us the conversion factor. If I were on a 10-hour flight from LA to Paris, traveling at 800 kilometers per hour, I would lose just under a nanosecond. Way too small to notice. But for faster-moving spacecraft, it can be quite significant and critically important. For example, orbiting GPS satellites travel at 3,874 meters per second with respect to the Earth. They use cesium atomic clocks to keep time. They measure time to within 1 second in 1,400,000 years. But these onboard clocks lose 7,214 nanoseconds a day due to time dilation. If onboard clocks aren't corrected regularly based on Lorentz time dilation formula, the position data they produce would be off by kilometers in less than a day.
Get NFL Sunday Ticket and...
Okay. All right. So he at the end there he talked about something. He talked about how much the GPS satellites lose. And there's another factor that he didn't talk about that is also involved in that, and that's the gravitation difference, which I touched on earlier, and I won't get into it that much, but the number he gave there wasn't exactly right. The number he gave was only for the speed dilation, which is what we're talking about now. There's another factor that influences those clocks, which is gravity, because they're further away from the center of Earth than people on the surface of the Earth are, and so their clocks would run faster because of that. And then one thing makes them go slower, the other thing makes them go faster, and depending upon where their orbit is, they could go faster or slower. But let me go back to this explanation, because it might be kind of difficult to grasp it here. All right, let me go ahead here. So I'll explain it one more time here. All right, just ignore all this stuff. This is complicated. I mean, it's you don't need to know all this. Okay, you just need to understand the basic concept here. So what's happening is he's got a big. Imagine this is a big, gigantic spaceship up in space. Okay, really tall spaceship. And he says it's 300,000 kilometers, or 150,000 kilometers. So the round trip going back up there and back would be 150 plus 150 is 300,000, which is what it takes, the distance that light can travel in a second. So he's set up a condition here where it takes light a second to go from the bottom of the spaceship up to the ceiling and hit a mirror and come back to the bottom again. So you imagine somebody in a big spaceship, they turn on a flashlight and they look up, and it takes a second for the light to get back down because it's so far up to the mirror and back. So gigantic spaceship. Takes 1 second to do that. Now the speed of light is constant for everybody. That was one of the rules, right? That was one of the assumptions that Einstein said. So if you assume that the speed of light is always the same, then when this giant spaceship moves through space really fast, about as fast as, close to the speed of light, this geometry here, just visually looking at this, it looks like he made it travel faster than the speed of light. But it's just, if it's traveling close to the speed of light, so not to scale, okay, not to scale. But if it was traveling close to the speed of light, 80% of the speed of light or something like that, then that light, instead of going straight up and down, it would have to go up to this point and then down to this point. You see how that would work? Because you're because this thing is traveling through space. And this right here, from here to here, is longer than here to here. See that? And if the speed of light is the same, if you get in a car and you're going 50 kilometers per hour, and you want to go 10 miles, it takes you so much time. But if you want to go 15 miles, it takes you longer. It's a longer time. So the speed of light is constant. It takes longer to get up there and back down again. Which means that time, in order to make that work out, time itself is going slower. Because of that. Because everything, at least outside of the atom, everything works by electromagnetic, which is light. It just turns out that what makes everything move, what makes my hands move, what makes when I push my hands together, why they don't go through each other, all that stuff is all done with electromagnetism, the electromagnetic force. And that's what light is. Light is a traveling wave of electromagnetic radiation. So everything works on that principle. And in fact, the title of Einstein's paper was something on the electrodynamics of moving bodies. I think was the original title of the thing. That's what it was all about. So in order to make the thing work, time goes slower. And that's kind of a difficult concept for people to understand. It seems like time is just a thing that just happens. There's 24 hours in a day, right? How can time go slower? But that's what it works out. When you figure it out, when you do the thought experiment, and it turns out that it actually happens when things go up in space and they go real fast. This is what happens. They go slower. Clocks in the spaceship, everything goes slower. And the thing is that because everything goes slower, if you were in a spaceship, all the electrodynamic stuff that's going on in your brain and everything is going to go slower. So to you, everything seems like it's going the correct speed. Isn't that weird? So for astronauts that are traveling really fast, to them it seems like everything's going the right speed. There's no problem. But from an outside observer, somebody who is looking at them, from Earth or from some reference frame, they call it a reference frame. If you're still, that's one reference frame. If you're moving, that's another reference frame. They're all different kinds of reference frames. But from somebody from an outside reference frame, inertial reference frame, it looks like everything is going slower. Time itself is going slower. And I'll talk just this thing right here, just to let you know. They use the Pythagorean theorem. You probably saw this in high school or even junior high, maybe. I don't know when they teach it. But it's a basic, right? You got a right angle triangle. This big long one they call the hypotenuse. This, and then they got these here. And so the square of the hypotenuse is equal to the square of the sum of these two. Right? That's the Pythagorean theorem. You've probably seen this before. Pythagorean's theorem. It's not that big. It's not that difficult of a concept unless you have to understand a little bit of math. Okay. But like if I square this line here, it makes a big square out like this. Do you see that? And if I square this one, it makes a square down here. And if I square the hypotenuse, it makes a square like that. And it turns out the area of this is equal to the area of these two. So the square of this side plus the square of this side equals the square of this side. And so with that, knowing that information, you can do a little algebra and figure out how much time slows down. How much difference there is between this and this. Right? This right here, that is, and actually 2 times, right? Because it's going back up and back. So the difference, you can figure out the ratio between this and this by using Pythagorean's theorem. and they work it all out, and they get a little formula, and it involves the speed of light, and they can figure out how much things slow down because of that. So that's pretty cool. Now there was another one here. Now that we showed that one, I think that kind of gets it. And it takes a while to understand this. You're not going to get this the first. If this is new to you, you've never heard of time dilation or any theory of relativity or anything like that. You're not going to get it the first time. It's really difficult. It's something that's hard to understand, and just the idea, of time going to it's just. I don't want to tell you that it's hard. Maybe it's easy. Maybe it's easy for you, but. Don't feel bad. Okay, don't feel bad if you don't understand it, because it's something that's hard to understand. That's all, and just over time, if you're interested in it, just from time to time, if you think about it, go watch a video on it somewhere. And some videos are better than others, and maybe they'll explain it a way that makes a little bit more sense. So with that said, let's go find another video here, because I do have another one. This one is, the audio on it is kind of messed up, so maybe I'll just play it and talk over it. I'm not sure. Let me go to this one here. Okay, and then we get a commercial. Yep. All right, here we go. Oh shit, I forgot to put it up on the thing here. There we go. Let me start this over.
So here we have Alice. She's standing inside a train, and with her is a light clock of some length L with a photon bouncing up and down at the speed of...
Okay, I'm gonna try. I'm gonna see if I can bump up that audio. Let's try it now.
Light. So here we have Alice. She's standing inside a train, and with her is a light clock of some length L with a photon bouncing up and down at the speed of light. So if we take one tick of this clock to be a round trip of the photon, how long will Alice measure this to be? Well, a round trip is a length 2L, and the photon travels that at speed c. So the total time is 2L divided by c. Now let's look at this from Bob's point of view. So Bob is standing on the tracks, watching this train go past at some speed v. So from Bob's point of view, things look a bit different. So the photon starts off over here, but the light clock is carried along by the train as it moves. So it hits the upper mirror here, and then returns to the lower mirror, completing the tick here. So from Bob's point of view, the path of the photon through the clock looks like this. So here we think about the second postulate of relativity. The speed of light is the same in all reference frames. So even though the light is moving diagonally, Bob should measure it to have the same value, c, that Alice measures. So in this case, what is the vertical velocity of the photon?
Okay, that's it. That's the guy's presentation. So yeah. I don't know if you could hear that or not. He was speaking a little bit more abstractly, rather than saying it takes 1 second and that kind of thing. He was speaking a little bit more abstractly, and he put a little bit of math up there. He said 2L for meaning the length going up and back, hitting the mirror and coming back, because it's two, right? It's got to go 1, 2, right? So it's two times the distance, and you put 2L, L meaning the length, the distance. So you get the idea, right? It's got to make that little triangular motion when something is moving along and it's going up and down. And this, for anything, if somebody was in a car, right? If you saw somebody in a car and they're driving by you in the car, and somebody in a car throws a ball up and it comes down and they catch it, it's going to do the same thing, right? The ball is going to go like this from your perspective. You know, from their perspective, it's just going up, straight up and down. From your perspective, it goes like this. It takes a longer path. And because light has a fixed speed for everybody, something's got to give, right? Because it's longer and it's time. So it's time runs more slowly. Let me play another one here. Let's see here. Oh, that gets into the twin paradox. That's a little bit more difficult. Okay, this is another one from the same same YouTube channel. Okay, this will probably be even more complex, but I'll go ahead and play it.
So here we have a plot of gamma, where the x-axis is velocity. So gamma is also called the Lorentz factor, and in the case we just looked at, it tells us the degree of time dilation between Alice and Bob. How much slower Bob sees Alice's clock ticking. Now, one thing to note is that because the velocity of any object is always less than the speed of light, gamma is always greater than 1. In fact, in our everyday life, v is much, much smaller than c, and so gamma is pretty much equal to 1. There is no observable time dilation, which is why you don't notice it when you go for a drive in the car. There is, however, a very famous experiment where scientists took 2 very precise atomic clocks, left one on the ground and sent the other in an aeroplane to fly all the way around the world, traveling really quickly. When they brought the 2 clocks back together, there was a noticeable difference in the timing between these 2, which was exactly what was predicted by relativity. Another thing is GPS satellites, which travel at around 4 kilometers per second relative to us. The clocks on board do tick noticeably slower than clocks down on the ground, and this time dilation has to be taken into account for the GPS on your phone to accurately find your position. We can see that for gamma to become physically noticeable to something other than an atomic clock or the computer on a GPS satellite, you need to be going very, very quickly. And it's only as v gets really close to c that gamma starts to grow large.
Drinking warm water before bed balances blood sugar levels.
All right. So that one again, he said that the GPS clocks run slower, but they don't. Let me find that that article. Here it is. All right, I'll bring this up here. Make sure nothing has changed here since I did it. Okay, I think we're okay. All right, this is they were talking about global positioning, and I just want to clarify that they were explaining that the clocks would tick slower because they're traveling faster, but because they're further away from Earth and they're in less gravity. The further, because gravity gets less as you get away from planets or anything, right? It's square the distance. So the further you get away from Earth, the less gravity there will be. And when you're in more gravity, your clock ticks slower, and when you're in less gravity, your clock ticks faster compared to somebody closer or further away. So for somebody on Earth, the satellite's clocks tick. Let's see if they say that here. They don't have it in the specs here. Shit. I thought they had it right in the specs there. Oh, there it is. There it is. Time. Detecting time slow. Okay, here it is. Okay. I'll just read this here. So, in 1955, Fredward Winterberg proposed a test of general relativity, detecting time slowing in a strong gravitational field using accurate atomic clocks placed in orbit inside artificial satellites. Okay. So Einstein, 50 years before, almost 50 years before that, 40 years or so before that, came up with this theory. And this guy, apparently in 1955, said, "Oh, I know how to test it. We can put them up high up in a high orbit outside of Earth's gravity, further away from Earth's gravity, and then their clocks will tick more quickly." So it says special and general relativity predict that clocks on GPS satellites, as observed by those on Earth, run 38 microseconds faster per day than those on Earth. Now, those other guys were saying it would be slower, right? We had two different YouTube videos where they said that it would tick slower in GPS. But they said that because they were just considering the speed. They weren't considering the gravity part of it. So it says the design of GPS corrects for this difference because without doing so, GPS calculated positions would accumulate errors of up to 10 kilometers per day. So, but they actually run faster up in space. But now the title of my thing said, "Why do astronauts age more slowly?" But here's this GPS going faster because it's up in space, right? Why would that be? Okay, it turns out because the GPS satellites are like 12,000 kilometers up. They're really, really far away from Earth. You know, they do it based on the center of Earth. People on the surface of Earth are closer to the center of Earth, and GPS satellites are really, really far away, which means they have a lot less gravity, which means their clocks will tick more quickly, and than those on Earth. And on Earth, the clocks tick more slowly than those up in space. But the astronauts, they're not way up there at 12,000 kilometers. They're only like a couple hundred kilometers, 200 to 300 kilometers. So they're just basically just skimming right over the top of the Earth. When you look at it at scale, I mean, it's like the thickness of an orange peel or something. They're really right next to Earth, so they're pretty much very close to the same distance from the center of Earth as people on the surface of the Earth is. There's not that much. There's a little bit of difference, but not that much. So the dominant effect in that situation is their speed. So their clocks will run slower at a low orbit like that. And it turns out that there is you can calculate all that, and somebody went and did that here and put it up on Creative Commons. This guy named P. Frondorf. I don't know. Thank you, P. Frondorf, for doing this. He's got this. All right, let me. I'll put this up on the screen so you can see it, if I can get OBS to cooperate. All right, here we go. There we go. Oh, it transitioned already. Look at that. All right, so somebody went and did all the calculations. This looks kind of complicated, but it's really not that. It's really not that complicated. So right there, two effects, right? Two different things that affect the clock of an astronaut or anybody or anything up in space. One is how fast they're going. All right, that's this one right here. Orbital speed, slow down, right? Because they're going fast, their clocks slow down. And here's the time here. They're doing it in picoseconds, which is really, really tiny per second. So it's not that much difference, but it's a little bit. So when they are close to you can't see the bottom of this thing. Shit. Let me see if I can get that. Oh, I know what to do. Here we go. There we go. Now you can see it. On the bottom here, let me get one more thing. There we go. So down here, the X coordinate is how far they are away from Earth's center. Because everything when they do gravity stuff, they do it from the center of the planets or the objects, you know. So at 0 here is the center of the Earth. Then on the surface of the Earth is right about here. That's the surface of Earth. But look at how close the space shuttle or the space station or whatever is just right here. It's not that much further up. You know, it's only a couple hundred kilometers up. 200-300 kilometers is how far it orbits. So there are two effects on that. One is their speed. When they're when you're close to the Earth, your orbital speed is fast, because you have to go fast to keep from falling in, right? So there's this dilation here, about 300 seconds or something, 300 picoseconds per second. So just because they're going so fast, it slows it down, their clock down. But then there's another effect, and that's the gravity speed up. As you get further and further away from Earth here, see, further and further away from Earth, then your clock will speed up because you're getting away from the gravity of Earth. So those two effects add up together, and then this guy who did this chart calculated it out and figured out what the net orbital time gain would be based on how far up you are in orbit. So for astronauts that are up in low Earth orbit, they call it, really close, just skimming the top of the atmosphere, their sum here, it shows that they are actually losing time. See, they're losing 200 to 300 picoseconds per second of Earth time. See, with regard to Earth time, that's what he was saying here. But when they get further and further away, like where the GPS is way up here, about 1,200 or something like that, or 12,000 rather. What was it, 12 or 13,000, something like that? GPS satellites, they're going to speed up about 200 nanoseconds, or picoseconds rather, per second, because their speed. But because they're far away from the Earth's gravity, the gravity part of it will make their clocks speed up rather than slow down. Did I say that correctly? God damn, I hope I'm not confusing you guys. So their clocks will slow down because they're moving. They're moving really fast. So their clocks are going to slow down because of that. But because they're far away from Earth's gravity, their clocks will speed up. And those two things cancel each other out to a certain extent. And when you add them together, at about 12,000 here, you follow that up, turns out their speed goes up. The net time gain is positive. So their clocks are running faster, the GPS satellites. So we saw two videos where they kind of misled a little bit, or gave incomplete answers. Let's say it that way. Give them the benefit of the doubt. They gave incomplete answers. So actually GPS satellites speed up. Mostly because of the difference in gravity, because they're further away from Earth's gravity. And that's when I did the review of Interstellar, that scene, where the guys they left one guy up in the mothership, and then the other guys went down close to where the black hole was. And they played a little ticking clock, and they had the ocean with the big wave. I don't know, you remember that, right? We just did that a few. You can look at my thing. Oh, hi, Peekaboo. Hi, how are you? This is a Twitch live stream. Twitch stream. If you're watching this on a VOD, this is a live Twitch stream, and they have a chat facility here where I can speak to the viewers, and the viewers can chat, speak back to me on this chat facility. And she says, let's see. Okay, so we got Peekaboo, who 10 minutes ago told me they were awake, and now just said, "Don't worry if you say something wrong. I most likely don't know." Oh, I'm good. How's you? Yeah, everything's weekend so far so good. I didn't stream yesterday. I took a day off, but I thought I'd do today's stream on science, and I thought this was a cool thing to do, time dilation. I don't know how much of it you saw, Peekaboo, but I want to try to be as accurate as possible because it's so hard to find good, particularly on this subject, to find like YouTube videos and stuff that actually present it in a way that's understandable and has accurate information. But those two videos that we showed so far, they mostly had good presentation. Those were the easiest ones I could find. There were a whole bunch of them out there that I didn't pick for my stream because they were too difficult to understand for people. There's a lot of math and stuff like that, so I didn't include those. But the ones I did include are a little bit understand, and it's just a hard thing to understand that time travels, that time is different. It's slower for some people in some reference frames, and it's faster for people in other reference frames. And that's why astronauts age more slowly. It's a tiny little bit. It's because astronauts in orbit, really they're going, like 20 kilometers per hour or something like that, or it's not. It's fast, but it's not anywhere close to the speed of light. But the idea now, there's a thing called the twin paradox, where one twin stays on Earth, the other one goes way out and travels close to the speed of light, to another star somewhere and comes back. And when they get back, the astronaut twin is young, and the twin that stayed on Earth is old because of that. And that's not the paradox. That's just the way time dilation works. But the paradox is that it's relative. So if all speed is relative, if there are two. If I'm up in space and I see something going by me like this, to me it looks like they're moving, right? But if you're in their spaceship and you're looking, it looks like I'm moving in the opposite direction, right? It's relative, and that's where the paradox comes in, because in the twin paradox, either twin could say, "Well, you're the one who's moving." You know what I'm saying? The one that goes out to the out in space really fast and comes back. From their perspective, it looks like the Earth is going away from them and coming back to them. It's relative, right? And so that's the paradox. How could one of them, if both of them would see each other would see the other one as their clocks running slower and being younger. That's the paradox. When I talk about the twin paradox, it's not just that they're different ages, it's that either one could say that the other one is running slower. And that's kind of complicated. That's the trying to explain that. I'm not going to try to explain that. I will maybe attempt that later. I've tried to find some videos that are really good about explaining, and there isn't an agreement. There's disagreement among physicists as to why that happened, or why the one on Earth would be the older one and the one who traveled in space would be the younger one, and they disagree about why that would be. So it's not a simple thing. It's difficult to understand that particular thing. This time dilation thing, I think, is, at least the speed part of it, is pretty easy to understand. I think intuitively, you get that idea that it's going in a little triangle. It's time light doesn't just go straight up and down, because the thing is moving. It's got to go in a triangle, so it's a longer distance. Light travels at the same speed for everybody, so it's got to take more time. So time runs slower for the person who's moving. That part of it, I think you can kind of get, even if you don't understand it right now, if you watch a few more videos and think about it over the next few months, and you'll understand that. What's weird is getting used to the idea that time runs differently for different people just because they're moving. It's hard for us to understand, because everything that we do is not even close to the speed of light. Everything, Even very fast airplanes and everything are not going that fast, so we don't notice it. And even for the astronauts that go up in space, or the satellites and stuff like that, we wouldn't notice it unless we had really accurate clocks. And that's why they notice it on GPS, because GPS has the accurate clocks that it uses. So that's why astronauts age more slowly, because they're low in orbit. Basically, if they were high up where the GPS was, then they would age more quickly. But if they like take a trip to Mars and come back, I'm not sure. It depends on how fast they go. I'm not sure, because they're going to be out. They're going to be away from gravity for a long time, which means their clocks are going to run faster because of that. So it depends upon how fast they travel on the trip. So it might be that the astronauts that go up into space, or to Mars, will end up their ages will age more quickly, because they're not going to be around gravity for a long time. So that's a possibility. I think that's what it is, actually, because they're not going to be around gravity. They're not going to be able to go that fast. Yeah, I think so. I think because it goes up to about 600 picoseconds there, and the other is only about 400. So yeah, I think their clocks are going to run a little bit faster on the trip to Mars. I'm guessing. I don't know for sure. I can look that up. But unless they really go really fast, much faster than they'd have to go much faster than orbital speed. And I don't think they do that. I don't think they go that fast. So yeah, I think their clocks will run actually faster when they're the Mars astronauts. But astronauts in the shuttle and in the International Space Station and all that, their clocks are running slower because of the speed, because they're orbital speed. That's it. That's why they do it. So does that make sense? I don't know. Let me see if I can find another video we can watch. Now they get more difficult as I go along here, so let me see here. All right, let me see if I can find another one here that we can watch, just to have just another perspective on it. Okay, so we did that one. Okay, we did that one, I think. Okay, I don't know what this one is. I put it at the bottom, so maybe it's not too good. Let's see here. I'll get by the ad, so I don't inflict the ad on you. All right. Oh, this one's funny. Okay. This is kind of cute. All right. I remember this one. So this is. Let me set this one up here. This is. This is by Jonathan Evans. It was 9 months ago. I'll do his whole thing here. And he did this in a kind of a cute little way, using stuffed animals and stuff to try to explain basically what we're talking about right now. So he put it in Creative Commons. So thank you, Jonathan Evans, for making your video available through Creative Commons for us. And I'll just play this video, and you have the background now from the other ones that we did. So now you get a feel for what what this is about. And this is this guy's funny way of explaining it. So,
my name's Gizmo, and I'm a pig. I want to tell you about a philosophical discussion I had the other day when I was on the train with my glamorous assistant. Boob. Boob, I said to him as we looked out of the window at the train on the other track. It looks like we're moving. Well, Boob had been getting very impatient and was very happy that we'd set off, but little did he know I was playing a cruel trick on him. Instead of our train setting off, the other train had started moving in the opposite direction, making it seem like we'd left. When he found out he'd been tricked, Boob was very grumpy, and he wouldn't talk to me for the first hour of our journey. He just stared out the window at his reflection in the silvered walls of the long tunnel through which our train was passing. About an hour into our journey, he asked me when we were going to set off. He hadn't realised that we'd already left, and he was becoming increasingly glum about the state of the country's ailing transport system. When I told him that we'd already left, he was very suspicious. It's true that you couldn't tell by looking out at the monotonous tunnel walls, and he didn't want to fall for another of my cunning tricks, so he asked me for conclusive scientific proof that we were moving. I thought for a minute, and then I came up with this answer. Imagine the light bouncing off your beady little eyes, hitting the wall, and then bouncing back again so that you can see your own reflection. Now, we already established in an earlier video that light travels and the speed is at about 299,800,000 meters per second. So let's call that number C for brevity. So how long does it take before you see your own reflection? Well, if the wall's about a metre away, which it was, it would take 1/c seconds for the light to get from you to the wall, and 1/c seconds for the light to get back again, which is a total of 2/c seconds, which is about 0.0000006 seconds. Now, since we're really moving, the light has to travel a little way along the track to keep up with us so that it comes back to your eye when you've moved. So it'll seem to take a bit longer before you see your own reflection, and we can say exactly how much longer by appealing to Pythagoras' theorem. So let's suppose that we're travelling at a speed v along the track. So, after some time, the light has reached the wall, and we've travelled vt along the track, at time t, and the light has travelled a distance ct, metres. And that's a little bit longer than 1 metre, because it's the hypotenuse of this triangle. So what we know is that 1 squared, which is 1, plus v squared t squared equals c squared t squared, which you can rearrange, and you find that the time it takes before your light is hitting the wall is t equals 1/square root of c squared minus v squared seconds. And it takes twice that long before it comes back to you. So the overall time is 2 divided by square root of c squared minus v squared seconds. And that's a little bit longer than 2/c. Of course, the difference is too small to measure, because our speed is so small with comparison to the speed of light. Nonetheless, Poob had brought his atomic clock with him on holiday, and he decided to spend the rest of the journey repeating this experiment. And he told me he kept getting the answer 2/c. I told him to stop being ridiculous, because either that meant we hadn't left yet, or it meant his brand new atomic clock that I'd bought him for Christmas was running slow. And anyway, we were nearly at the destination, so could you give me a hand with the bag, please? He's been gibbering about it ever since. He doesn't think it's possible to do an experiment that will conclusively prove you're moving. And he hasn't left bed for 3 weeks because he's worried it'll make his clock run slow. What's that, Poob? You've just compared your clock with Eek's watch. And he's a little bit ahead of you. And he didn't come on holiday with us. Don't be ridiculous, Poob. You probably just dropped yours in the loo. Join us next time for an exposition of Smale's alpha theory, and we'll ask this expert whether stable homotopy theory is all it's cracked up to be. My
Okay.
name's Gizmo, and I'm a pig.
All right, Gizmo. All right, so that was that one. That was. It's the same thing, just. So that was, he made it kind of funny and cute, and put a little bit more math in there. But it's the same deal, you know. Now another thing that happens when anything in a reference frame goes fast like that, close to the speed of light, is called length contraction, which is really bizarre, maybe even more bizarre than time slowing down. And that's along the direction that the thing moves, it shrinks. so like if you had this pencil or this pen that's traveling along at the speed of light, or close to the speed of light, 0.8 or whatever times the speed of light. From our perspective, from the outside looking at that thing, it would shrink in its length along that path. It wouldn't shrink this way or this way, this dimension. Only the direction that it's traveling. It would shrink, and it would actually be shorter. And that's really weird. And it's the same kind of idea, but it's a little bit more complicated to explain. So I won't explain it. But it's the same idea that that you have the speed of light and you're moving, and you work it all out, and not only does your time slow down, but also the length. And it's not just your length; it's the length all along that path. So, like if you're traveling from here to some planet on another star somewhere, and you're going close to the speed of light, the distance to that star is going to be shorter for you. I mean, from your perspective, it won't be, but from an outside observer, it's going to be a shorter distance that you have to travel. It won't seem that way to you because your clock is going slower, right? But it actually is a shorter distance. So I don't know if that makes sense. I think that makes sense. So that was those. So next thing I'll try to do is to get into the twin paradox, which is a little bit more complicated. And I think it would be too much to do that right now. We'll just go with this right now, and then like part 2 or something, we'll talk about the twin paradox and why and how different physicists try to resolve that paradox. And the paradox isn't what we just talked about. Remember, the paradox is not that the astronaut's clock is going slower and the astronaut is aging different. The paradox is that either the person on the ground or the person in the spaceship could say that the other one's clock is going slower because everything is relative. The spaceship, for the person on the ground, the spaceship is traveling away and coming back. From the spaceship, they could say, okay, I'm the center, I'm the reference frame, and the Earth is going away from me and coming back. Which sounds kind of weird, but that's the way it is, And the way they resolve that is, well, I'll get into that later. It's kind of complicated. Some say it has to do with the acceleration, because the spaceship has to accelerate and then decelerate and turn around and come back, and they say that acceleration has something to do with it. And others say that it has to do with changing reference frame, because when it's going away, it's in one reference frame. When it's coming back, it's in a different reference frame. And when they shift reference frames, that changes it. So there are different ideas that people have as to why that is, how to resolve that paradox. But I guess they all agree that if somebody got in a spaceship and went away, traveling close to the speed of light, and went to to another star system or something and came back, their twin who was left on Earth would be older than they would be. They all agree on that, I guess, but they're just not sure why. I think there is a real answer to it. I'm sure Einstein understood it at the end there. He figured out, because it was a paradox to Einstein too. When somebody first brought it up, I forget who it was who brought it up first, but Einstein said, "Yeah, that's a paradox, but that's the way it is, And then later on, they figured it out. So, all right, that's pretty much all I got. Yeah, I think that's it. Yeah, that about covers it. So, well, next time we do a science stream, I'll talk about the actual twin paradox, and we'll go over some of the different YouTube videos that there are out there that talk about it, and what they're, how they try to resolve it. And there is a big debate, as to what actually causes that. And there are different ways of trying to resolve that, and different thought experiments and everything else to try to figure it out. So that should be interesting. Before we talk about that, you kind of have to understand this. You have to understand time dilation itself. You have to understand that there's, for something that is moving relative to to an outside observer, their clock runs slower. You got to understand that much at least. So before we get onto the twin paradox. Okay, Peekaboo, I missed your chat here a little bit. You gave some smart pig. Oh yeah, that's smart pig. Yep. Yeah, little stuffed animals that talk. How about that? Oh my goodness. Yeah, that was a cute little video. And then just to make it, then he put in the heavy math at the end of it, made it just to make it a little bit more digestible, I guess. All right, so we're gonna wrap it up here. Yeah, everybody follow. I did a shout out for Peekaboo Draws. They have a stream where they draw, basically just showing hands and showing drawing and stuff like that. I haven't seen your stream in a while, Peekaboo. I guess you haven't done any streams lately, but I got you followed. So when you do a stream, if I see that you're streaming, I'll pop in for sure. So yeah, everybody give them a follow. Peekaboo Draws on Twitch. And yeah, if you want to give me, I'm still trying to get affiliates. So while you're at it, give me a follow too. If you can get to Twitch, it's really easy to get. Oh, let's see. Peekaboo says, I've been on a break, but hopefully starting again soon. Oh, great. Okay, good. Yeah, I noticed a lot of people got to do that. You got to take a break. Life happens. You got to take some time out. I took off yesterday just because, for whatever. So yeah, you got to take time off sometimes. So yeah, if you're watching this VOD, get to Twitch if you can, and follow me. If you don't have a Twitch account, it's really easy. You just enter an email. And I don't even think you need to even verify the email to follow. I think you just enter the email and it lets you in, and you can just follow the channel. So that would be helpful. And I do mostly this kind of stuff, science and technology, but a lot of other stuff too. I do, like tomorrow I'll do news. Mondays turn out to be the news day, so I'll do news and civics and that kind of stuff. And I also do IRL streams once in a while around here in New Hampshire. I do, talk about animals, because I got a lot of animals around here, so I talk about those guys. and veganism and a few other things. So yeah, variety of stuff, but mostly science and tech. So all right, so let me let's wrap this up now. I'm not gonna rate anybody. So I will try to do this is a new closing. It's a little bit different because from the other closing. I still have all the credits in there just in case. But all right, I appreciate everybody stopping in and all people watching the VOD. Everybody take care. We'll see you later. Bye.
All right, here we go.
First thing we climb.
Oh, sorry. That was the wrong one. Oh my goodness. All right, let me try again. All right, I guess I'll just do the. I did the credit. Oh, here it is. Credit closing scenario. Sorry about that. All right, let's try this again. Thank you all for joining. Bye.